Hello everyone. We're going to continue our discussion on eigenvectors and eigenvalues. So let's get started. So in the previous session, we already discussed the equation AV equals lambda V. In this equation, we already know A is the matrix, V is the eigenvector, lambda is the eigenvalue. Now we want to see how we can represent eigenvectors and eigenvalues geometrically in this session. So I have a diagram here where we have V as a vector. We don't know if it's eigen or not at this point in time. We have another value AV here, which is in line with the vector V. So if the points V and AV are in line with the origin, that is they are in the straight line or they are collinear, then V is an eigenvector. However, if you do not have AW in line with the vector W, which is passing through the origin, they have to be in straight line. If it's not in straight line, then W is not an eigenvector. That is how you can figure out if a vector is eigenvector or not, by representing them geometrically. If V, the vector itself, and the transformation of the vector through the matrix, that is AV, if they are in straight line passing through the origin, then that means that the vector V is an eigenvector. If it does not, that means that it's not an eigenvector. So to say that AV equals lambda V means that AV and lambda V are collinear with the origin, because AV has to be in line with V, which has to be in line with the origin, and since AV equals lambda V, so I can also write this as this. So even lambda V has to be collinear. So an eigenvector of A is a non-zero vector. Important point is non-zero. It has to be a non-zero vector V such that AV and V lie on the same line through the origin. We've already seen this here. In this case, AV is the scalar multiple of V. The eigenvalue is the scaling factor. How is that? Because AV equals lambda V, and we've already seen lambda is a scalar value through which the vector has been scaled or multiplied. The direction, however, remains the same. We just discussed this in the previous session. So this is the scaling factor. Let's take some example here. So we have a transformation function from R2 to R2, which is from two-dimensional space to two-dimensional space, be the linear transformation that reflects over the line L. So this is the line L, and we've defined it by y equals minus x, and let A be the matrix for T. So the matrix for the transformation is represented as A. Let's say if I take x as 2, 3 and 4, corresponding y becomes minus 2, minus 3 and minus 4. So this basically means that we are mapping from positive to negative end, right? That means U and AU are not in line with the origin, as you can see, because this is here and this is here. That means a reflection is not an eigenvector, because if it would have been here, AU, or if U was here, somewhere here, in line with the origin, then this would have been this would have been an eigenvector. But since they're not in same lines, this is not an example of eigenvector. So U here is not an eigenvector. Let's take another example. So here we have AV, 0, V all in the same straight line. The length is also equal. That means that the eigenvalue of AV equals the eigenvalue of V, which has to be 1 obviously. And then only the direction has been changed. So it's pretty much still an eigenvector. So V is an eigenvector because they're still in the straight line. However, just the direction has been changed. Given AV equals V in magnitude, that means the eigenvalue is 1. But the direction is reversed, so we represent the eigenvalue here as minus 1 because the direction is reversed. So that's pretty much it for this example. And let's take another example here. W is in line with the origin O, which is in line L, and AW coincides W. So pretty much this is coinciding this, but still AW is in line with W and O. Despite the fact that it is coinciding, it's still in line. So this W is also an eigenvector. Just a quick note here, the vector W is an eigenvector because AW is collinear with W and the origin. Indeed, AW is equal to W, as you can see, because it's coinciding. This means that W is an eigenvector with an eigenvalue of 1. All eigenvectors lie either on the line, so whatever the equation of the line is, either the eigenvectors will lie on that line or on a line perpendicular to L. The vectors on L have an eigenvalue of 1, so anything which is lying on the straight line itself of the equation has an eigenvalue of 1, and the vectors perpendicular to L have an eigenvalue of -1. So something important comes handy when you have to apply machine learning problems or computer vision problems. You can just keep this in mind. Yeah, if it's not too much to remember. But even if you forget, you can always geometrically, plot your vectors and the multiplicative value of your vectors and see if it actually is collinear and then solve it. That's fine too. We've seen this. So projection example, so let T again be the transformation function from R2 to R2, be a linear transformation that projects a vector vertically onto the x-axis. And let A be the matrix for T. So we have the matrix A, which is doing the transformation T over an R2 from R2 plane, that is two-dimensional plane, over on the x-axis. So this value is projecting here on the x-axis. This is not an example. U is not an eigenvector here because they're not in straight line. Here Z is projecting on the x-axis AZ, but this is also not an example of projection because they're not in straight line. Then let's take the third one. Here V is projecting on x-axis, which is passing through origin, and AV is also pretty much on the origin, so they're in the same straight line. V is an eigenvector. Similarly here W and AW are in straight line with the origin and they are coinciding, but still given they are in the straight line, that means W is an eigenvector. So this is how you identify when you have an eigenvector and when you don't. This is pretty much it for this session. In the next session, we will be discussing eigenspaces, which is again a very important topic. How I would want to conclude eigenvalues and eigenvector shortly is eigenvector is a vector which does not change its direction when you pass it through any kind of transformation or function. The direction remains constant. However, the scaling value might change, and the change in the value is given by lambda, which we've already seen. Geometrically, eigenvector is in line with the origin, and then when you do the transformation, that is when lambda v is also plotted or AV is also plotted, it's in line with the origin. So they're all collinear, the vector, AV and origin. If it's not in line, that means your given vector is not an eigenvector. This is how you geometrically understand if a vector is eigenvector or not. So I've concluded the discussion on eigenvectors and eigenvalues. I hope this makes sense. In the next session, like I said, we will be discussing eigenspaces, which will need understanding of eigenvectors. This will be a slightly tricky topic to understand, but I hope, I'm sure that you'll get hang of it once we start discussing that in the next session. So if you have any questions up until at this point in time, feel free to write them in the comment section and get in touch to me through the website. And yeah, thank you so much.